When you hear the word computer, what do you think of? I bet it's your laptop, right? Or maybe your smartphone. But what if I told you that some of the most powerful and important computers in history, well, they had no screens, no keyboards, and they didn't even use ones and zeros? Let's dive into this hidden world of computing.
Yeah, it sounds pretty much impossible, doesn't it? I mean, our entire modern world runs on digital logic. But to really get our heads around what a computer is, at its core, we have to kind of strip away everything we think we know and travel back to a time when computation was a physical, almost mechanical thing.
And that journey takes us to our very first major category, the analog computer. Back in the middle of the 20th century, this was the undisputed heavyweight champion of computation.
So the analog era really had its heyday, back in the 1950s and 60s. This was long before our current digital world took over everything. And look, this wasn't just a different kind of technology. It was a completely different way of thinking about how to solve problems.
So, what even is it? Well, an analog computer doesn't think in neat little numbers like 1, 2, or 3. Instead, it works with data that flows, that's continuous, kind of like the temperature slowly rising in a room or the voltage changing in a circuit. It measures things, it doesn't count them.
And believe me, these machines were everywhere. They were the secret brains inside really complex systems like aircraft and submarines, calculating flight paths in real time. But you also had one in your family car. A speedometer is a perfect, simple analog computer. It translates the continuous rotation of your wheels directly into your speed. No ones and zeros needed.
And this, right here, this gets to the very heart of the difference between them. Think of analog as a smooth ramp. It's a continuous flowing incline. Digital, on the other hand, is like a staircase. It's made of distinct, separate steps. These are two totally different ways of modeling the world around us.
And that brings us to the staircase, the digital revolution. Now, this is the world we all live in and know so well, a world built entirely on those discrete little steps, ones and zeros.
Yep, from the smartphone in your pocket to the giant servers that run the internet, these are all digital computers. What they do is take every single piece of information, a photo, a song, a number, and they just chop it up into a massive, massive string of binary code.
But digital computer isn't a one-size-fits-all kind of term. There's a whole ladder of power here. It starts with the microcomputer on your desk, then it climbs up through minicomputers that handle business data, all the way to the huge mainframes that are the backbone of global banking and air travel. And at the very, very top, you've got the titans, supercomputers, tackling enormous challenges like predicting weather patterns or mapping the entire human genome. Just incredible.
So we have the ramp and we have the staircase. But what happens when you need both? What if a problem requires you to walk the ramp and climb the stairs at the same time? Well, that's where our third and maybe the most fascinating category comes in, the hybrid computer.
A hybrid computer is, well, it's pretty much exactly what it sounds like. It takes the analog system's amazing ability to process real-world continuous data, and it mashes that together with the digital system's raw power for logic and precise counting. It's a specialist, built for incredibly complex jobs. And you've probably used a hybrid computer without even realizing it. Like every time you fill up your car. The pump sensor measures the actual physical flow of fuel, right? That's the analog part. Then, a processor instantly converts that flowing liquid into a precise number of gallons and a final price. That's the digital part. It's such a simple but brilliant blend of both worlds working together. This combination gives them some unique superpowers. They can translate data between the analog and digital worlds insanely fast. This lets them do high-speed, real-time analysis with pinpoint accuracy. These things are built for immediate, precise feedback on what's happening in the physical world. And because they're so good at that, you find them in places where the stakes are incredibly high. They run industrial control systems in aerospace. They power medical devices like MRI scanners that turn physical signals into detailed images of our bodies. And they even simulate wildly complex systems like nuclear reactors. And here's something you might not expect, a real curveball. In certain situations, hybrid systems can actually be more energy efficient. By letting the analog parts handle what they're naturally good at, processing physical signals directly, the whole system can save power. It's a great reminder that the newest tech isn't always the most efficient tool for every single job.
Okay, so after this little journey through computing history, what's the big picture here? Well, it's that there isn't one best kind of computer. Instead, there's a specific kind of computer for every type of problem.
It really just boils down to this.
Analog computers, they're perfect for simulating continuous physical systems. Digital computers, they are the absolute masters of general all-purpose computing. And hybrid computers, they are the champions of complex problems that need to connect the physical and the numerical worlds in real time.
So the really crucial takeaway here is this. Thinking about computers isn't about which one is better. It's about which one is the right tool for the job. You wouldn't use a hammer to turn a screw, right? In the same way, you wouldn't use a purely digital system when you need to perfectly simulate a continuous physical process.
And that kind of leaves us with a final thought to chew on. As we face bigger and more complex challenges, things like climate modeling or advanced medical diagnostics, problems that are a messy blend of the physical world and the data world, are we going to find that we need to think more like a hybrid computer, combining the best of both worlds to build the solutions of the future?